We'd like to start Moore's Lobby a little bit differently today. We want to acknowledge the March 24th passing of a true titan of the semiconductor industry, Dr. Gordon Moore. Few people, if any, have had such a monumental and lasting impact on the technology and companies that have revolutionized our entire world. And of course, our podcast name, Moore's Lobby, is an homage to Moore's Law, the observation made by Dr. Moore in 1965 that the number of transistors on chips was doubling every year. A decade later, he amended the rate to every 2 years, but Moore's Law became an almost self-fulfilling prophecy that has seen the number of transistors on a microprocessor increase from about 20 in 1965 to over 20 billion today. Moore was born on January 3, 1929, and grew up to join Shockley Semiconductor in 1956, where he worked on improving processes for silicon device manufacturing, something very relevant to today's episode. A year later, Moore and 7 others left Shockley to found Fairchild Semiconductor, a company that would leave a lasting impact on the semiconductor industry and the growth of that local area in California that eventually became known as Silicon Valley. Moore was the director of R&D at Fairchild, where in 1960, the team built a circuit with 4 transistors on a single wafer of silicon, creating the first silicon integrated circuit. In 1968, Moore and colleague Robert Noyce left Fairchild Semiconductor to form a new company that later became Intel. Over the subsequent decades at Intel, Moore served as executive vice president, chairman, and CEO. During Moore's time at Intel, the company grew to dominate the microprocessor world, becoming the heart of the coming personal computer revolution. The industry was truly dominated by Intel Inside. Over the years, Moore received numerous awards recognizing his notable achievements. He was elected a member of the National Academy of Engineering and the National Inventors Hall of Fame. Moore received the IEEE Medal of Honor, the National Medal of Technology and Innovation, and the Presidential Medal of Freedom, the United States' highest civilian honor. Beyond his technical work, Dr. Moore and his wife, Betty, were generous philanthropists to universities, technical endeavors like the 30-meter telescope, nursing education, and environmental conservation. From the PCs and smartphones that record and play this podcast to the data cloud that stores the information and the networks that carry all this data, all of us here at All About Circuits and Moore's Lobby are indebted to the pioneering work of Dr. Gordon Moore. Over his 94 years, he left an indelible legacy on the semiconductor industry that we cherish. So this, and in some sense, all of our Moore's Lobby episodes are dedicated to Dr. Gordon Moore. And now on to episode 62 of Moore's Lobby.
Photonics versus electronics is a disruption analogous to electric cars and gas cars. It's inevitable. You just can't predict when it happens.
From EE Tech Media and All About Circuits, this is Moore's Lobby. I'm your host, Daniel Bogdanoff. Today in the lobby, we're joined by Dr. Thomas Mader. Tom is the COO of OpenLight, a new independent company formed out of investments from Synopsys and Juniper Networks. While you might be unfamiliar with OpenLight, you're definitely familiar with some of Tom's other work. Well, at Intel, he founded a project codenamed LightPeak, later named Thunderbolt. He also worked on several interesting projects while at Amazon, including the Amazon Dash button. Tom, I'm really excited to have you in the lobby today. I was told you have a connection to the namesake of this podcast, but that's all I know. Can you tell me more?
Indeed. Yeah, my uncle, my mom's brother, was the first in his family to go to college, immigrated here from Switzerland, and he took a job at Fairchild in the 60s. So his boss was Gordon Moore. So he worked with all those Intel guys before they became Intel.
So is that part of the family what got you excited about and into tech and engineering?
Yeah, well, I went into engineering back when it wasn't cool to be an engineer. But my dad was an engineer. My uncle was an engineer, so I had a bit of a head start. But I got absolutely fascinated by electric guitars back when I was a kid. And that actually, electric guitars, distortion pedals, and amps is what really got my interest, to a feverish level. I really wanted to know how to do it.
So did you then go and get a degree in electrical engineering, and that was kind of an inspiration for that?
Absolutely. I was curious how to generate the sound you want to get from an electric guitar, and all the different sounds you hear from different bands with electric guitars. And that was the beginning of my kind of obsession almost. And I knew a little bit because my dad was an engineer and my uncle, but that's what really drove me to it.
Yeah, I'm fascinated by the similarities between audio engineering and RF engineering. There's a really interesting and surprising amount of crossover.
There is, and there's strong analogies, as you say. Yeah.
So where'd you go to school and what did you focus on for undergrad?
Yeah, I went to Berkeley for my undergrad, electrical engineering and computer science. They had a program that essentially has both together. And then grad school, I went to Colorado, University of Colorado.
I'm in Colorado as well, so represent over here.
Nice, nice.
What did you focus on for your PhD?
My PhD was focused on electromagnetics, so very high speed electronics and wireless electronics, that type of thing. So I was working on very high efficiency, very high frequency electronics.
I hear you made the rounds as an intern.
I did a whole lot of interns. I did my sophomore year at Berkeley, my junior year at Berkeley, my between grad school, one in grad school. So I did at least 4 internships, which is kind of odd, I suppose. 5.
Wow. Can you give me the rundown of where you interned and maybe a highlight from each of those?
Happy to do it. My first one was at Siemens in Switzerland. It's a German company. My dad, Swiss, and connected me there. I did one at Apple for 2 summers. And then I did one at a company called Macom back in Boston.
I hear you worked on developing a patent as an intern, which seems unusual to me. Is that true?
Yes, it is true. My second summer at Apple, there was a problem of reflections on an interface from the computers. This thing, nobody would know this anymore. There's a thing called a SCSI bus way back before USB. SCSI sounds so wonderful, right? SCSI. And they had problems with reflections on certain devices that they connect. They had to terminate the ends, which, back then, this is megahertz speeds. And I came up with a little circuit that automatically figures out whether something's plugged in or not. And it actually puts a termination or removes a termination at the edge of the board. And I was able to do it with transistors that were already in the bill of materials. So it only cost a few cents. So it was a pretty nice one, and we decided to patent it. So it was kind of cool.
That's very cool. And then what was your first job out of grad school?
Out of grad school, with my PhD, freshly minted PhD in electromagnetics, I went to Hughes Space and Communications, working on satellite electronics down in the LA area.
And that lasted a couple years, and you moved to a startup called Light Logic. What did you do there?
Yeah, it was a packaging, a robot to do alignment of fibers to lasers. So it was, instead of humans doing it, it was a robotic approach. And I was brought in as the high-speed guy to make it go fast.
And then you got acquired by Intel from there. Is that correct?
We did. We made a product, and I got a transceiver product going, and between that and the packaging, we got acquired by Intel in spring of 2001. It was a wonderful event.
Can you tell me how that transition went and what that meant for your technology path in your career?
It was great. I got the experience of being integrated into a big company as a startup, the whole kinds of learnings. Got to meet Craig Barrett one time, and it was really cool. We got to actually get our stuff into some volume. We got to sell hundreds of thousands of units, and I was able to meet other people. That's actually, during my time at Intel, I met the Silicon Photonics team there, and I even moved to sit with them so that we could work together. So that's when I first learned about Silicon Photonics, was back then.
I understand you were a part of the creation of Thunderbolt as a technology. And when I plugged my phone in a moment ago to my monitor to charge it up, I got a Thunderbolt warning, and I'm wondering if that's maybe your fault.
I don't know if that's good or bad, but yeah, maybe. Yeah, it was an interesting thing because I was running this big engineering team, and then I decided to pivot. Things had shifted, and moved and changed, and I moved into a role where I was more of a principal type of role. And what I noticed is that the data port and the video port were 2 different ports. And the video ports back in those days were 1,000,001 ports, right? Everyone had their own standard, HDMI, DisplayPort, DVI, and then you had the old VGA. And it's like, wait, what? There should be one. And yet everybody thought it's their one. But I thought, Intel is in a unique position because Intel was driving the USB standard. And I thought, why don't we take the USB standard, add video to it, make it one port, one port to serve them all. And that was where the idea for Light Peak came. Of course, me being an optics guy, I said, if you made it an optical port, you'd never have to change that connector ever again in theory, or change it once every 20 years. That was the idea. So Light Peak began as one port, data and video, and hey, let's make it optical. That was what we were trying to do.
That's must have been pretty revolutionary at the time. How was that received?
It took some work to get it. It's a large company is like steering a large ship, right?
Yeah.
And it takes a while. So the fellow named Mario Canicia, who was running the Photonics team, he introduced me to a bunch of people there, which was actually very useful, helped me get connected. And we were able to get the ship to turn a bit. And, it just made sense, right? It made sense to combine those ports together, and it made sense to find a port that could do both. And eventually, as you know, Apple adopted this, right? And it became Thunderbolt. That was a process that took some time and some convincing. Yeah, it's a different job to convince someone of it. It did get adopted, but it wasn't optical, right? So I got half.
Yeah.
Right? We got those ports to combine. That's good. And USB-C these days has things all in one. You can now charge through it and all that. So the beginnings of that, I feel happy about that. The optical was maybe a little ahead of its time.
Why do you think the world wasn't ready for optics? And when will the world be ready for optics? Because we're still on, Type C, one port to rule them all. It's all copper.
Yeah, indeed. It's a funny thing. Sometimes incumbent technologies stick around a lot longer than you think. And incandescent bulbs, hey, now LEDs are starting to really replace them, right? Electric cars, gas cars, pencils, right? Pencils and paper, which I write with pencils. That's the way I view it. It's a big disruption. I think photonics versus electronics is a disruption analogous to electric cars and gas cars, or, LEDs and incandescents. It's inevitable. You just can't predict when it happens. And it's because it is very different. The kind of people that design electronics are not the kind of people designing optics.
Yeah, but there's so much crossover. Again, it comes back to the distortion pedals again.
Yeah, all comes back to distortion pedals and electric guitars.
Yeah. If we do it right, it does, I think. So you've been at Apple, you've been at Intel, you also in some startups, but you spent time at Amazon. What did you work on at Amazon?
Amazon was a really cool gig, and I was running a team that was called it was originally called Emerging Technologies. The team had struggled to get any wins. They were formed to go and prototype Jeff ideas, which were disrupting the engineering team. But they never really had anything get off the ground. It was more like, let's go prototype and look into, but they were frustrated. I was able to get actually some things off the ground that actually came out of the team, and we showed Jeff and et cetera. So we turned it into concept engineering because we wanted to be, these are concepts or engineering them. So we turned it into concept engineering. And yeah, it was coming up with new things and helping evaluate new things that came down and bringing things forward up.
Did you have products that saw the light of day?
There were several. Maybe the best known was this thing that ended up being the Amazon Dash button. We were able to get that pitched and going, and it's literally was a button with a battery in it. You push the button and it places an order for toilet paper or coffee or whatever it is. And we actually got that all the way through. We got it approved by Jeff. We got a sponsor in the .com side, and we shipped those things, and they shipped quite a few of them. And it was a really cool project. So yeah, that was one. We did a bunch of other little things. There was a little wand we made that you could scan groceries, and you could use your voice, or you could scan a barcode. We had several others. There was a page turning feature on an e-reader. Really cool stuff. I thought it was really fun. It was a really fun gig.
So this must involve the Entrepreneur in Residence program. Can you tell me more about that?
Yeah, we thought, we were a concepting group. We designed prototypes, tried to get the risk out, get executives to say yes, to give the budget. But ultimately, when you hand something to an engineering team, the engineering team is in the middle of doing their stuff, and they don't have engineers. Even if they have the budget, they don't always have people to work on it. And what happened is, whether it was the button, whether it was the wand, whether it was the page turn feature, we basically had to take my whole team and go insert myself and my team into that engineering team so that it wouldn't die on the vine. It's the old, the valley of death, right, for a new innovation. So what we did is we actually created an entrepreneur in residence position where the person was designed to go with the project to the engineering team because they know everything. They can drive, give continuity without having to suck my whole entire team over there. And there was some success with that. We did that on the button, and that worked pretty well.
I'm personally very curious about the Amazon Dash button, and I want to hear more, but first it's time for a quick break. We'll be right back. This episode is brought to you by Molex. Molex interconnect solutions have the expertise and quality you rely on for industries from automotive and healthcare to consumer. Now you can have dependable solutions and flexibility with the Molex Fit family of connectors. Molex Fit connectors eliminate misalignment, protect contacts from critical damage, ensure proper and long-term performance and reliability. Molex, powering the connected world. Learn more about Molex reliable and secure interconnected solutions at avnet.com/Molex-connected-world. That's avnet.com/Molex-connected-world. We're back with Dr. Tom Mader, COO of OpenLight. Tom, when the Amazon Dash button came out, it was sort of like the poster child for IoT and the future of what IoT devices could be. What was the reception like, and did that project go the way you thought it would?
No project ever goes exactly how you think it will.
Fair.
But it was pretty cool, pretty fun. We had a lot of fun with it. We even made a version that was the AWS button that you could use to do something in Amazon Web Services, and that never got volume. So it was really cool. The idea was, you have this button and it costs a few dollars to make it. It actually had a battery life of years because you push it, you turn it on, it connects to Amazon, it places the order. And if you do that short enough, which you want for the customer anyway, light blinks, and that's just a few seconds of battery life, right? So it was a really cool kind of new thing. I would say that after a while, I think just having millions of these buttons in your house, I think, at some point, it became, well, wait a minute, we can actually build this into software buttons. And I think, which is kind of funny, right?
I see where this is going. Yes.
But Amazon started to put it like little buttons on the app, and they put little buttons on the Alexas. And honestly, that's fine. I think that was just a way of thinking about shortcuts, thinking about making things simple. And it was, how do we make things as simple as possible? There was another thing that came out of that, which was a thing called the Alexa Connect Kit, which most people don't know about, but you can Google it on Amazon. It's a chip that connects to Amazon, and it was designed as being something that you can design, smart Christmas trees and control them through Alexa. And it's just a little module that you can put into something, and it has cloud backend and everything. And that was actually a cool one, I thought. Alexa, I believe that program's still going.
Interesting. So that almost feels like something that would ultimately end up in like every smart plug or every smart device just as a component.
Yeah. Huh. And in fact, we were able to get that into the smart microwave that they made. I think was the first place we put it. It was just a shortcut for people to be able to make smart devices easily, because otherwise you're doing the same thing over and over again. Solving Bluetooth problems, solving Wi-Fi problems is horribly painful. Do it once, right? You're doing the same thing over and over again. So we tried to make it a shortcut, cloud backend. And of course, you can buy things and you can connect to it. So it's the downstreaming impact and all that fun stuff. Right?
Yeah, I'm thinking the AWS button seems like a great way to get a project greenlit that's been having trouble. It's like, no, it has AWS hooks.
Yeah, exactly. Those are fun projects.
But then it seems like you have come back around to your maybe second love after guitars. It would be optics. And you're now at OpenLight.
Indeed.
Can you tell me about OpenLight and what you do there and a little bit about the company?
Absolutely. And as you say, photonics and also really high speed stuff, right? Watch things go fast. And yeah, OpenLight is a self-contained startup. We are co-owned by Juniper and Synopsys. Synopsys has a larger stake, but we run as an independent startup, and we are all about this. Again, it is a photonic technology. It is a silicon photonic technology, and we are bringing this to the world in what we call an open platform.
Can you level me up a bit? What is silicon photonics? What are they, and what's new and trending there?
In the electronic world, way back when, in the 40s, 50s, and 60s, transistors were invented, and they were individual parts, right? And in the old days, you'd have a 5-transistor radio. The integrated circuit, which Intel actually pioneered, was everything on one chip, right? And that's an old story, right? And now you have billions of chips on it. Photonics and optics has been in the single transistor space for a long time. You have one laser, another laser, another laser. Silicon photonics is bringing photonic functions all on a single chip. And people do photonic integrated circuits in all indium phosphide, or they do it all in silicon. Indium phosphide is expensive, brittle, difficult, but people do it. And that's great. Silicon photonics is using silicon to guide light, modulate light, detect light, and you can make complex devices. So you can get a lot of elements all on one chip, just like in the electronic space. However, one of the challenges is silicon does not generate or amplify light. You need indium phosphide or some other material. So Intel also has a similar technology. We have a technology like this that literally brings indium phosphide and silicon molecularly bonded, and we can actually have both indium phosphide and silicon on our wafers.
Fascinating. On the same wafer.
Well, it's a wafer. There's little pieces of indium phosphide that get molecularly bonded down.
Fascinating.
So you do the silicon, you put the little things, you bond them molecularly, and then you process those. And then you have what is essentially a chip, a photonic integrated circuit with active elements, optical amplifiers, optical modulators, and optical lasers.
I guess who needs a packaging team if you can just stick your wafers to your dies together, right?
Yeah, right. And you can just draw it down on your design, right? Hey, I want a laser here. Hey, I want
That's crazy.
Optical amplifier here. I want, et cetera. You still need to get it out to a fiber, right? You don't get around that. But everything else you can do on the chip.
Are you able to expound on how that molecular bond works? I imagine like a lot of polishing and then some maybe heat and special chemicals, or what does that take?
I could tell you all about it, but of course, then I'd have to kill you.
Right. Understood. Understood.
I'm not the expert on that either, so I probably couldn't even tell you about it. But it is cool stuff. Yeah, but it is a molecular bond. So there's a set of things that have to happen to make that happen properly and at high yield.
That's very, very interesting. And then you mentioned making it more open. Can you tell me more about what that means for OpenLight and just for the world of engineering at large?
When we say we're the first open silicon photonics platform, we're the first open silicon photonics platform that has the lasers and amplifiers integrated on the chip. If you go to, Tower and Global Foundries and all these companies, AMF, there's companies out there with silicon photonics, they do not have lasers integrated. You can go design and make wafers, so they're open. But there's only one other company that I am aware of that is in production that has the monolithic laser on the chip. That is Intel. But to date, they've been making end products, and that's great. They're making transceivers, they're LiDAR, there's all these things that they're vertically integrated. So if you think about the old days of ARM versus Intel, right? Oh, it's an ARM processor. No, it's an Intel processor. But it's not ARM versus Intel. Intel was selling processors. ARM was licensing. So it's an Apple processor or a Samsung processor. We're kind of like the ARM here. And again, Intel may decide to open their thing up, but today we're the open one. You can design your own chip.
Do people then take the IP and integrate it into their chips, or are you creating almost components that people would throw onto a board of some type?
It's called a PDK, process development kit. We create components that are then available at Tower. This is a Tower semiconductor process. So Tower, when a customer goes to Tower says, here's the PDK, and you can design into it's Tower's process, right? Not OpenLight, it's Tower's. But it's under license from OpenLight. A lot like ARM, right? If you go to a foundry and say, hey, I want an ARM core, they say, yep, okay, work it out, make sure you have the license, and et cetera. And then, okay, now you have an ARM core on your chip. Hey, we're just saying now you got a laser on your chip.
That sounds pretty straightforward. What are some of the more common applications for this, and what are some that have surprised you?
Yeah, it's a good question. And it is very interesting. We had come from Juniper. We were part of Juniper until we were spun out. Of course, datacom and telecom. And that is a first place. There's a lot of standardization. That world of datacom, hyperscale interconnects at the big data centers, that has already been going to silicon photonics, moving towards silicon photonics with the larger numbers of lanes. Intel's playing in that space. We knew that. That was not a surprise. And that is our first market, is to go after datacom. We have a lot of interest from LiDAR customers, and in particular, the so-called coherent LiDAR. And it was interesting that the optical amplifier is what's most interesting to them, because they're trying to get a lot of power out. And if you have a passive chip, you have to put a huge amount of power here to get a trickle out over here. And if you could put an amplifier on your chip and regenerate on the chip, it's a big advantage. So that's what we hear. So a lot of interest in LiDAR. The other one that we see emerging is we call it compute interconnect, right? Whether it's between GPUs or disaggregating memory from a processor. There's a little bit of noise. There's some companies that are focusing on that. There's the IR labs of the world and such, and there's this emerging place there. That one we believe is a big one. And what we're doing in the datacom plus some, we believe is going to very well leverage into that. So the compute interconnects, we believe there will be a good big volume there for us.
So when I think of fiber, typically I'm thinking of undersea cable or a network in a city. What is different about doing optical interconnects inside a server or a PC even?
Interestingly, in the compute XPU, right? Whether it's the GPU, memory, CPU, you name it, they're used to all being, everything on a chip, or there are two chips right next to each other, and it's breaking out of the centimeter interconnect and going to the meter interconnect, right? So instead of, like you say, an undersea cable, they may only need 1 meter or 5 meters. So it's very short, but it's getting into that fiber allows them to just go a few meters, which suddenly changes the game. Now, getting into optics is the game, and then it's a shorter distance, but latency becomes very important, is what we've been told, right? So making sure that it's just the time of flight, that you don't have too much processing in between. So yeah, it's latency, and it's getting into the fiber just for a few meters, and power, right? I mean, always power and cost.
Yeah,
power cost. Well, power's king, right? When it comes to very high density interconnects. So yeah, we've got to keep on that.
What is OpenLight's take on LiDAR? It's been kind of a darling, but also certain people have spoken against it in the past. I'm curious where you see that technology going in 5 years and even in 50 years.
I view LiDAR as something that is, in my view, inevitable. I believe self-driving cars are inevitable, but we just talked about how long it takes for optics to take off and light bulbs and pencils. I don't know if I'm retired by the time self-driving cars are ubiquitous, or if it happens in 5 years. I just don't know that. So yeah, the timing's a question, right? But yeah, it seems like an inevitable thing.
Good answer. You sound like someone who's been in tech for a while.
But again, just my take is, I don't need LiDAR. I need LiDAR. I don't need LiDAR. Look, my take is these sensors will all get really cheap and ubiquitous. And whatever you can put on there, if it gives you another 9 of safety, it's going to go on there. Whether it's LiDAR, camera, radar, you name it, they're all going to go on there. They're all going to get cheap. They're all going to get integrated on a chip, because it's another 9 of safety and one less person that gets killed on the road. My take is inevitably you're going to want all the sensors you can get, and they're all going to be cheap.
Yeah. No, I like that. There's no technology that will be dominant because we need them all, but they all have their own advantages.
And there's a few, you asked about there's these optical computing startups that are trying to do computing in the optical domain. There's companies looking at doing health applications. I'm kind of excited about this long tail of other applications, and it is kind of fun to see them, and we can't talk about it publicly. They're private companies are doing their own thing, but it's really cool to see, optics can do various sensor things, they can do various compute things. So it'll be fun to see that evolve, and it is really cool to be able to see that.
Coming at it from an electrical engineering perspective and speaking to other electrical engineers, what do we need to know about optics and how it will impact the future?
Optics is coming, and some people say optics is here. If you're a software engineer, you're not going to care. But if you're a hardware engineer, it's a good idea to be aware of it. There are always new technologies that come. Quantum computing comes to mind. Again, just like LiDAR, self-driving cars, fascinating. And if you're at the beginning of your career, look at some of these things. Photonics, yeah, in silicon photonics, it's happening. It is actually happening. And it's a pretty cool thing to go into if you're at the beginning of your career.
You came out of Juniper and it's co-owned. How does the direction you get from your stakeholders influence the future of OpenLight? Does it focus you more in that comm space? And how much flexibility do you get in the design and R&D process?
I believe that we were set up as an independent entity specifically so that we could go sort out this business model and be free to, again, use tools from Synopsys. We have a very close relationship. If a customer needs a different tool, we need to support it to figure out our business model. And that is exactly why. And whether it's LiDAR or optical computing or sensing, this is one of the reasons we are an independent entity to sort this out. We are given a lot of freedom. And of course, we do look for opportunities that benefit our owners, of course, right? So we do that. But at the same time, we have a set of customers. We're serving our customers. We're focused on customers. Whatever we need to do to serve those customers, that's what we do.
So on the PDK front then, because I imagine most of your customers, if not all of them, are using these PDKs. You talked a little bit about what they were. How does an OpenLight PDK look the same and different from a more standard one like a ARM processor, like you mentioned earlier?
The standard, so again, it's evolving to where more complex and highly capable tools are coming on board, right? And companies like Synopsys are working on that. The biggest difference in our PDK is that we have a laser and we have an amplifier, and you can just draw it and then it shows up on your chip, right? So that's the big one. But we are also pushing, because having lasers, amplifiers, and these more complicated devices, and moving to higher density, large lane counts, and larger functions, we also believe that you need the higher order abilities, the EDA tools that are more like electronics. Otherwise, you're not going to be able to do your design right the first time. You're going to get lost in it. So nobody today is going to cut Rubolift to make a Intel processor, right? So we believe it's important. We also believe it's important.
Can you provide the context of that for folks who are unfamiliar of cutting Rubolift?
Yeah, I'm not an expert on this, but I believe in the old days, what I've heard is people were, using, to resist, to figure out where the transistor is and where you etch and where you don't etch. They were doing this by hand, almost like, think of it like masking tape. It wasn't masking tape, but something like that, to figure out where the light goes and where the light doesn't go. And then over time, it became automated machines and big, lithography machines controlled by software tools, by, companies like Synopsys and Cadence. And it's this big automated designed thing now that you don't go cutting things by hand.
Thank you. So what does EDA look like and design and simulation look like for lasers? Are there any gotchas or surprises there that people should be aware of?
Well, with a laser, then again, people in the field know to know this. We can, we have a schematic, which is an optical schematic. You drop down a laser, waveguides, modulators, etc. Then there's a layout. That's very analogous to the electrical domain. But just like in the electrical domain, people understand that transistors can oscillate, or if you making an amplifier, it can be an oscillator. If it's an oscillator, it's an amplifier. Murphy's Law says you design one, you get the other. I would say in the optical space, you have to be a little bit careful of certain things like reflections back into the laser, and ensuring your laser is tolerant of reflections, and making sure some of the things interact properly, the link budget, there's not too much loss, things like that, making sure things don't talk to each other. A lot of them are very analogous, but it is a little different in the optical space.
What sort of conversations did you have to have with fabs to make sure that things were coming out matching the EDA? We
do a lot of testing. Testing is a large part of what we do, and modeling. And we work very closely with the foundry, with the folks at Tower. It's very much experimental together with theory. Always theory and experiment have to coexist, but we do a lot of testing to make sure it's right. So you don't just do theory for this kind of thing. It's both.
I will go way too deep, way too fast into testing. But can you talk me through the testing process a little bit? What sort of parameters are you looking for, and what makes a good one versus a bad one?
That's a good question. For the laser, of course, you want single mode output that's clean with low noise. You also want to make sure it works over temperature, over time, and that it doesn't have mode hops and things like that. You want to make sure it's stable. For a modulator, you want to make sure it has the bandwidth. And not only that it has the bandwidth, resistance, capacitance, inductance, you want to make sure that when you make 1 million of them, that they're all the same. So we have to look at corner lots and such. So yeah, there's other things, but that gives an idea.
Can you talk me through the block diagram of the whole system? Because as you were saying that, I realized I don't fully have a mental model of what it takes for an optical system end to end.
Absolutely. For ours, for let's say a datacom link, you would start with a laser, and the laser creates the light into the waveguide. And then from the laser through the waveguide goes to the modulator. And the modulator essentially is like a chopper. It's chopping the light, turning it on and off. And that's your modulation. Light means a 1 and no light means a 0. And then if you do high order modulation, it might be a quarter, it might be 1. From the modulator, then you may go through various couplers where you have a little bit of a measurement to look at your power. You may measure wavelength through a wavelength selective device, but generally then you go out through a coupler into the fiber. So essentially you generate light, you modulate light, you might measure it, and then you're out through a coupler. On the receive side, it's more or less couple light in and go into the modulator. Oftentimes there's a little bit of a measurement, power, usually not wavelength at that point.
In my head, I was thinking, like phase shifting and quadrature amplitude modulation and that sort of thing, but it's more just a power is generally where this focuses.
The datacom space is chopping the light on, off, or PAM4, which is 4 levels, right? That's happening both in the electrical domain and the optical domain, right? The very high speed, 100 gigabit, 200 gigabit. Electrical has gone to 4 levels. Optics is also doing 4 levels. There is a lot of higher order modulation. Our LiDAR customers, the ones that are coming to us, are generally the coherent guys, and the coherent guys do phase modulation. So in that case, in the case of LiDAR, yes, it's phase and it's a coherent where the signal coming back is mixed with the transmit signal and you can get much better performance. There's also coherent communications, which we're looking at for down the road. So yeah, a lot of the bread and butter is on and off, but the LiDAR guys are looking at phase modulation, and for some of the future stuff and in the long haul space today, they do a lot of the advanced modulations just like they do in the electrical.
And then how do you scale a system like this? How do you make sure that it is consistent, that the frequency is the same and the whole thing plays together at 1 million chips instead of 1,000 chips? One
thing is you work with a company like Tower who knows how to do that, right? They know how to scale, and they can really get their process dialed in. They're the experts at that. At the same time, you run various corner lots. You make sure you look at what you think that the corner lots are going to be, slow and fast, just like you did in electronics, and lots of testing, and check out lots of lots and make sure things aren't varying. Yeah, it's a lot of brute force, plus I think with our partner Tower, their experience.
And that makes sense. I guess the whole point of IP is to work with people who have done the legwork already, so it seems to fit well here. As we sadly start to wrap up, we like to do a lightning round at the end of each episode. And I was going to ask you who you think the best guitarist is of all time, but I think a better question is which guitarist had the best tone of all time?
Well, I was going to say me. But, I will say, especially when I was young, the Boston, that Tom Schultz fellow, that dude had a rockin' sound. Yeah, it's got to be him.
Okay. Good answer. I approve. Best concert you've been to?
I'd say I went to a Pink Floyd concert that I think I'll have to rate that one. They had some pretty entertaining stuff there.
Their light shows, optics, yeah. And then they get the Pink Floyd lasers. I check.
Yeah, you have a big pig or whatever, right? It was super entertaining.
Any advice for future engineers, either college students, early career, mid career, who want to be successful as the world develops and changes? Any advice and key skills that you think they should pick up?
Well, I would say go into plastics. I'm kidding. Isn't that what people said in the 60s? Right? Sorry. I mean, honestly, you can't lose going into software. Software will continue to be a big thing, but if you're interested in hardware, there is so much exciting stuff. Yes, silicon photonics, quantum computing. There's an amazing amount of really cool stuff happening out there, especially at the beginning of the career, and you want to dig into something pretty cool. There's a lot of stuff. But yeah, silicon photonics, you won't go wrong with that.
And then if you hadn't become an engineer and you couldn't be a guitar player, what would your career be? What would you do?
Oh, you just took away the second one, be a guitar
player.
I
had to make it harder for you.
I did consider going into law. I actually considered even combining engineering with law and becoming a patent attorney. I did consider that seriously for a little while, and then I said, yeah, I'm an engineer guy. Let me stick with engineering.
I thought about that too, and it's like, that sounds really boring when I realized what that actually means. Like you'd see a lot of cool technologies. You'd see a lot of cool technologies, but
you'd see a lot of really cool technologies, but I like to create the technologies.
Yes.
But on the other hand, look, I'm sure there's a patent attorney listening in, and I'm
sure
sounds like a really cool gig. So, but
yes, yeah. If you're a patent attorney and you're listening, hit us up on social and tell us the favorite part of your job. We'd love to hear it.
Yeah.
Awesome. Well, this has been really wonderful. Thank you so much for your time.
Thank you. It's been really fun.
That was Dr. Tom Mader, Chief Operating Officer of OpenLight. If you like this episode, come visit us on the Moore's Lobby social pages and tag someone who you think will also like this episode. We're sending Moore's Lobby swag to folks that do. I'm actually drinking from my Moore's Lobby coffee cup right now. Yeah, a little Moore's Lobby ASMR for you. I'm so sorry. Also, make sure you're subscribed in your favorite podcast tool and on the All About Circuits YouTube channel. I love that I get to do this podcast and bring you these tech explorations or techsplorations. Thank you for listening. We wouldn't get to do it without you. I'm your host, Daniel Bogdanoff, and I'll catch you next time.